In section 5.2, we're talking about perpendicular bisectors, and specifically we'll be looking at perpendicular bisectors in triangles. So, to get started, what is a perpendicular bisector? Well, first of all, what does it mean for two lines to be perpendicular? Because that word was part of it. Well, we know that perpendicular means that two lines meet at a right angle or cross at a right angle. Illustrated here. Two lines are perpendicular if they meet to form right angles. I don't know why that's being so slow. Sorry. Well, it's a perpendicular bisector, right? So then what does that word bisect mean, or what does it mean to bisect a segment? Remember that word bisect means cut in half, cut into two congruent parts. So, as illustrated here, we're bisecting a segment if we are cutting it in half by passing through the midpoint. Therefore, if this would be a bisector of the segment, we can see that that's true by the congruent tick marks, making this point where those intersect the midpoint of that segment. So, to be a perpendicular bisector, it must do both things. It must cross a segment at a right angle through that midpoint in order that it cuts it in half or bisects it. And the definition here for perpendicular bisector. Again, we're just fulfilling both requirements, that it be perpendicular to a segment, meaning it crosses at a right angle, and that it bisect this segment, meaning it cuts it in half into two congruent segments. So we're going to be looking at perpendicular bisectors today and properties of perpendicular bisectors. Word we need to know for this next definition is equidistant, and you basically have the word equal and distance, so equidistant means equal distance or the same distance. We need to know that term for perpendicular bisector theorem. Again, we know a perpendicular bisector intersects a segment at a right angle, that's what makes it perpendicular, and it intersects at the midpoint so that it cuts that segment in half into two congruent segments. That's what makes it a bisector. Now, perpendicular bisector theorem tells us that if a point is on the perpendicular bisector of a segment, then that point is equidistant from the endpoints of the segment. Alright, let's decipher that for the picture here. If a point is on the perpendicular bisector of a segment, we have this point C, which is on the perpendicular bisector of this segment AB. So we have this point on the perpendicular bisector. Then we know that this point C is equidistant, or the same distance, from the endpoints of the segment, meaning C is the same distance from A and B. So if I were to draw segments from A and B to C, those are congruent segments. Only if that point C is on the perpendicular bisector of the segment would these be the same distance. And this not only holds true for this point C, but you could put any point on the perpendicular bisector. How about this is point D? Well, that means if D is on the perpendicular bisector, then it is also equidistant from points A and B, the endpoints of the segment that is perpendicularly bisected. So these two segments, to point D from A and B, would be congruent as well. And the same would apply for any point on the perpendicular bisector below that line, that these segments drawn to that point, or going to the endpoints, would also be congruent. Any point on a perpendicular bisector is equidistant to the endpoints of a segment, so it's kind of neat. And I want to show you why this is true, or how this is true. Let's say for a second that we had a line that went through that midpoint. I'm going to change the color here to make this a little more obvious. Okay, we'll do that in red. Let's say for a second, this is a bisector, right? Because it goes through the midpoint. However, this is not perpendicular. But our points on here, just because it goes through the midpoint, our points on here equidistant to the endpoints. If you consider any point that I would put, imagine putting points on this line, are they closer to A or B? Well, anything on this line is going to be closer to A because it's leaning that way. If I go below this line and I put any point on here, all of these are going to be closer to which endpoint, A or B? And you should be thinking, well, all of these are closer to B because it's leaning that way. So being a bisector is not enough. Also, being perpendicular is not enough. This is at a right angle to that line, but every point on here is closer to which point, A or B? Well, everyone here is closer to A. And if I went this side of the midpoint, every point on here is now closer to B. So being perpendicular isn't enough, but when you have a perpendicular bisector, as we did here, perpendicular and a bisector, then any point on it is equidistant from the endpoints. This is a really powerful theorem. Okay, it tells you a lot and it will help you discover a lot. Perpendicular bisectors are very awesome. Any point is equidistant to the two endpoints. This is just the converse of the perpendicular bisector theorem. Remember that converse switches around the if and then of a conditional statement. And so we're saying if we have a point equidistant from the endpoints of a segment, like here, we have this point D, which is equidistant from the endpoints of a segment. I know it's equidistant because I have two segments drawn where they are congruent. So let's see, if this point D is equidistant from the endpoints of a segment, it is, it's equidistant to A and B, then I know that that point D, it has to be on the perpendicular bisector of the segment. So I know that through point D, if I drew this line, I know that it is both perpendicular and a bisector of that segment. It has to be. And I could extend this and make it a line or extend that segment, but I know that D is on the perpendicular bisector of the segment AB because that point D was equidistant to A and B. If it had not been the same distance, then it wouldn't be on the perpendicular bisector. Alright, so that's the converse. It works both ways. Points, on a perpendicular bisector equidistant to the endpoints of a segment. Let's use that in some examples. I'm given here that line RS, that's this line, is the perpendicular bisector of segment PQ. So this thing is being perpendicularly bisected by this line RS. So let's do some markings here. If RS, this line, is a perpendicular bisector, then it is perpendicular to PQ, and it bisects PQ, meaning it cuts segment PQ in half, making two congruent segments. So, find X and Y. Well, if it's a bisector, then I know that these were congruent. I marked those as such. So then shouldn't 4Y be equal to 12? Right? Those segments are congruent because it was a bisector. Divide by 4, and we find that Y is equal to 3. What about with X? Alright, this uses perpendicular bisector theorem. RS is a perpendicular bisector. Point R is on that perpendicular bisector, therefore it is equidistant to points P and Q. Because it's on that perpendicular bisector, it's equidistant to the endpoints of that segment that it perpendicularly bisects. Therefore, these segments are also congruent, and I know that their lengths are the same, so I know that that 8x minus 9 should be equal to or the same as 6x. Solve for x, I would probably subtract 8x, get rid of it here, and we'd just have negative 9. 6x minus 8x would be negative 2x. Divide by negative 2, it'd be negative 9 over negative 2, turning to positive 9 halves. Or as a decimal, 4.5 for x. Alright, perpendicular bisector theorem there. Another example. They tell you line JM is the perpendicular bisector of line segment HK. Let's mark everything we know. Line JM, that's this, is the perpendicular bisector of line segment HK. So it's the perpendicular, meaning at a right angle. Bisector of HK means it crosses at midpoint M, and these would be congruent. And the question here is which lengths in the diagram are equal? Well, because it was a bisector, I already marked HM and KM congruent. I know that because of the definition of bisect. So line segment HM is congruent to line segment KM. But what else do you know? If point J is on the perpendicular bisector of this segment, then that point J is going to be the same distance from those endpoints H and K. I'll mark that as such, and I'll write that segment JH is congruent to segment JK because it's on the perpendicular bisector of segment HK. It's equidistant to the endpoints. And one more question on this example is point L on line JM. Here's point L, and I don't know for sure because I don't see it extended through the point, but is it on line JM? Would it be? Well, let's see. If JM is the perpendicular bisector, L would only be on that perpendicular bisector if it was equidistant to the endpoints of that segment that JM perpendicularly bisected, which was segment HK. Is L equidistant to H and K? Yes, it is. We look at the fact that the distance to H and K is the same, and since L is equidistant to H and K, the endpoints of that segment, it is on the perpendicular bisector. Perpendicular, there's the symbol for that, bisector. So yes, it is on line JM. That's actually the converse of the perpendicular bisector theorem, as we just discussed. If a point's equidistant to the endpoints of a segment, it's on the perpendicular bisector. Okay, we got all our basics done with perpendicular bisectors, knowing that any point on the perpendicular bisector is equidistant to the endpoints of the segment that it perpendicularly bisects.